We begin a new section in this video. This is quite different from what we did previously in the section 1 to section 5. In those sections, the increment is a constant, meaning when we talk about, say, increasing or decreasing here, so the amount is a constant. So either we have an increasing annuity or decreasing annuity, the amount of increase or the amount of decrease is a constant. Mathematically speaking, in the previous 5 sections, we deal with arithmetic sequences. So the change is a constant. In section 6, we deal with compound increasing annuities. From a mathematical angle, we have the ratio being a constant. So for instance, I go from 1, let's say 1.05, 1.05 squared. Right, this is what we call compound increasing. Right, the ratio between two consecutive numbers is 1.05. So here is ratio. It's a constant. This corresponds to the geometric sequences we studied before, right? So having this in mind, in this video, we study sequences that either increase or decrease by a constant ratio instead of by a constant amount. So this is particularly what I just explained, right? The default setup in the previous studies will be like this. 1, let's say this is the payment at the end of year 1. A2 is the payment at the end of year 2, etc. So it's 1, 2, 3 all the way to n. The change of amount is 1. And now we want to study the compound increasing case. So you start with 1, 1 plus e, 1 plus e to the power of t minus 1, etc. So here the ratio 1 minus e, 1 plus e, excuse me. So it's very clear that compound increasing, forms a geometric sequence. We already studied geometric sequence in chapter 2. So much of the content we are about to learn is probably not that new to you. So this is the PV analysis. We already let's find some place to draw the timeline. So at time 1, payment is 1. At time 2, payment is 1 plus e. At time 3, payment is 1 plus e squared. Goes on and on. At the final point, the payment is 1 plus e to the power of n minus 1. Okay. So this is usually what I do in the first step. Draw a timeline and label all the points at the corresponding time points. Okay, so like $1 is at time 1, like 1 plus e is at time 2. So now we want to know the present value. Present value here is the first two, the value at the beginning of this special annuity. So for the first payment, $1. So it's actually 1 times V. In order to convert the amount of $1 at time 1 to time 0, you need to times by the 1-year discount factor V, right? So similarly for the second payment, 1 plus E at time 2, we need to times by the 2-year discounting factor, so the V to the second. And so on, this is the last one. Right. So let's put double arrow to say this is how we get this summation sequence. I always say, this should be the second step. You, when you try to solve a question, right? First step to draw a timeline. Second step to write down all the terms you are supposed to be summed up, right? And then you analyze. So in here, if you pay a little attention, you will see this is a geometric sequence, right? And the ratio is this is the ratio, right? So, well, you can easily see, right? The first term is V. If V times R is exactly the second term, and the second term times by R will be exactly the third term, etc. Here we do a little, well, let's call that transformation. If you look at this original partial summation, the power of 1 plus E does not match the power of V, right? It's actually mismatched by 1. So what we want, or what we think of, is we can times everything or all the terms by 1 plus E. Of course, we will need to divide by the same factor to keep it the same. After doing this, we are able to have both V and 1 plus E in the same order, right? So that's why here's order 1, order 2, goes all the way to order n. And then we introduce U to denote this. So U is the whole thing. Then the inside the bracket, it becomes U plus U squared plus all the way to U to the nth. Does this look familiar to you? If not, I can write it V plus V squared plus all the way to V the nth. This is the present value of an annuity immediate of n year. Okay, now let's do a comparison. The form looks identical, except now it's not V, but U, right? And what is V? V is 1 divided by 1 plus I. So now I have U down here. U is obviously different from V. And immediately what I can think of is maybe I need to introduce a new interest rate, right? So I is the original interest rate, effective interest rate per year. And there is a 1-to-1 correspondence between I and V. Now I have U. So I'm trying to find the interest rate to match this U such that U is the new discounting factor. Right? In order to make that happen, I just need to establish this equality. Right? So I want my U to be the new discounting factor. Then I will need to get a new interest rate. Or we can call this either imaginary, or I think the textbook calls this net interest rate. Okay, what it does is by introducing this new interest rate J, your U will be the 1 year discounting factor. So this is new V under J. Right. So originally is the discounting factor V is defined with respect to the interest rate I. Now I introduce a new interest rate such that its corresponding discount factor is U. Okay, with that in mind, this whole thing becomes the annuity immediate of n years. But now let me write it in a different color. Right. So here is the special place at the new interest rate. Okay. With that, we can easily derive the relation between J and everything else down here. I is the original interest rate. E is the ratio of your increment for the payment. So from here, we can see J is bigger than 0 if I is bigger than E. So the interest rate is supposed to be bigger than the increasing ratio, okay? So from here, what we do is we can, so basically to this step, we already derived the present value, right? So we just need to sum everything up. Inside part is a new annuity immediate. And then the rest is, well, you just need to times by this factor 1 over 1 plus e. And then we can write it out the next. So this whole thing is obviously a angle n at j, right? And we have this nice result for j. For the question will give you I and e. So with I and e given, you can easily compute j. Okay, after you have j, you can calculate the formula inside the box. Then you know the PV formula. Okay, now let's do an example to see how it works. 3.9 is the example. 3.9, if you have textbook, you should go to page 77. 3.9. Jack receives a payment at the end of each year for 10 years. The first payment is $1,500. The remaining payments increase by 6% compounded each time. Calculate the PV of the payments at time 0 using an annual effective rate of 10.24%. So as you can see, I is bigger than E. The first payment is 1,500 and N is 10. Okay. So here what we have is, well, if you want to draw a timeline, it will be like this. Okay. So at time 1, you have 15. Then it will be 1,500 times 1.06, right? Goes on until the final moment. The payment will be 1,500 times 1 plus 0.6 to the power of 9. That's because, if you look at 1, there is no 1.06, so you can think that it's 0's power, right? So 0's power corresponds to 1. Once the first corresponds to the second year, so obviously, the power term corresponding to the 10th year would be the 9th. Okay. We want to know the present value. By the way, we don't have a dedicated notation for the PV of compound increasing annuity. Okay, so let's just use PV of this special annuity. Right, the second step, at least in my approach, is to write down all the terms. Right, 1,500 is at year 1, so times by 1 year discounting factor. Goes on. Okay, obviously you can factor out 1,500 for everything, right? And if you want, you can even factor out V if you want, because it's in every term. At this step, well, I think some of you probably would like to apply the formula we just derived, which means you're going to calculate J first, right, and then plug everything in. Well, that always works, right? But usually, what I do is, because I really don't want to have you memorize a lot of formulas. So let's write it out. So inside the bracket is obviously a geometric sequence. And the ratio of this particular geometric sequence is 1.06 times V, right? And the first term is V, 1 minus this ratio. And then we need to count how many terms we have, right? Well, it's easy, right? 1, 2, all the way to 10, so I have 10 terms. So throughout this course, I mentioned many times that if you really want to say there is a formula for this cost, it would be the partial sum of a geometric sequence. The rest is based on this simple result. So now let's take, no, not that. That's not my interest rate. So let me move this to the other side and get the eraser for. So my interest rate is not 6%, it's 10.24%. One minus 1.06 divided by 1. Right. At this stage, you can times by the denominator, so it becomes 1.1024, and then you should be able to get the answer. By the way, let me use the built-in calculator to show you, usually how I calculate this thing. Well, it's my, so let's. So let's do a quick calculation, okay? The way I usually do it is I like to compute everything in one step. I don't like to write down anything in between, but that takes some training, okay? So let's start with the numerator. So it's 1 minus, you have a lot of things, right? So technically speaking, you should put another bracket down here, right? So it's 1 minus bracket, another bracket, 1.06 divided by 1.1024, put the first bracket. So this gives me the ratio, okay, this fraction. And then I need to raise the power to the 10th, okay, put another bracket. Then it will finish everything inside this part, this whole term. And then I need to click on equals, because then it will do the subtraction, 1 minus the whole thing. So as you can see, it's 1 minus that. So that's the numerator. Then I just need to divide by the denominator. Right? Again, I'm going to do the subtraction. So I need to put the bracket to change the order of operation. Minus 1.06, put bracket. Okay, so that's the denominator. Hit enter, that will do the computation. Then times by 1500. Okay, so that is the final result. As you could expect, that is exactly the same as what you get from the textbook after applying their formula. So that's 3.9. That concludes for the this part, and then let's move on to do the annuity due. So once you have the formula for annuity immediate, well, annuity due it's almost trivial, right? What you need to do is right, the denominator part. So if you do a quick comparison, you will see. First of all, this is the standard annuity due, right? But at different interest rate. So that's the reason I don't use D, because in our notation, D is defined for I, right? And we know D is I divided by 1 plus I. Okay, so if you look at this formula, it's J divided by 1 plus J. So it's the corresponding D, right, for the interest rate J, right? So, but we don't want to use the same D for a different interest rate. That is why, I keep this as J divided by 1 plus J. Okay. I leave this to you, which means I want you to do the analysis. So we know the difference is the first dollar is paid at time 0, so there's no need to discount that. The next is 1 plus E. Here is 1 plus E square, goes on. Right. The last payment is paid at the end of n minus 1 or at the beginning of n. right? Then you should be able to write down the PV, right? So the 1 plus something, okay? Please complete, okay? And use usually what we know to derive the formula. Again, this is a geometric, right? So you don't even need to do what I showed here. So what I showed is here, right? So so basically what we're trying to do in the whole some a little messy mathematical results down here is to connect compound increasing with a standard annuity, right? And we try everything indeed we are able to achieve this, right? So it's given down here. But as I showed in example 3.9, you can simply write down the summation and apply geometric, right? It works the same. And the huge advantage is most of you can, after a few tries, well, shouldn't have difficult, like understanding the sum of geometric, right? Then, once you know this result, everything, goes rather smoothly, right? So, it's the calculator doing the final step. And with this, you can easily get the final result. There's no need to go through that whole thing. You do have a built-in function from your financial calculator to calculate this A angle N. That could help, but of course, in general, from the learning perspective, what I did here for example 3.9, it's likely to be a better strategy, because if you understand this approach, you should be able to apply this anytime. Okay. What's the examples for this part? 3.10 and 3.11. Let's look at 3.10. That's page 78. Geo receives payments at the start of each of the next 20 years. The first payment is $400, which is paid now. The payments from then on increase at a rate of 15% each year, using an annual effective rate of 23.05% from the PV. So it's obviously a compound increasing annuity due, because the first payment is made at time 0. At time 0, $400. At time 1 is 400 times 1.15, because it increased by 15%. Okay, the payment lasts for the next 20 years, which means the last payment is at 19. Okay, so to the power of 19th, we want to know the present value. Right? So this is 400, write it down, plus 400 times 1.15 divided by V, goes times by V, excuse me, times goes all the way to the last one, we discount by 19. So let's factor out 400 and put things inside. What do we have is, all right. So inside the big round bracket is obviously the partial sum of a geometric sequence. 1 minus 1. So interest rate is 23.05. 1 minus the first term is 1, so I skip it. To 20s. Okay, it's not 19. 20 is the number of those terms. Right, this is order 0 to 19. You have 20 terms. Okay, you can easily get the result, right? 10 seconds or 20 seconds at most. I don't like you to actually apply whatever the formula textbook gives you. It actually has a formula, but it's not something I would like you to use. Okay, but if you really want to apply, the formula is here. Okay, you you get J first. For instance, for our example here, you're going to do I, which is 0.2305 minus, this is E, excuse me, I minus E is 15%. Okay, then you need to divide by 1 plus E is 1.15. Then you will get J to be 7%. The good thing with this is once you get 7%, you do have the formula from your, you can click on a few buttons from your financial calculator to get the result. But please remember, this is an annuity due. So you will actually need to change the beginning time on your financial calculator. It probably involves second function. So use the menu from your calculator to practice. Example 3.11 is easy because now they want you to calculate the accumulated value. Once you know PV, AV is nothing but PV times 1 point. The interest rate is 2305 raised to the power of 20. So AV is always at the end of your annuity. So although the last payment is made at 0.19, the end of this annuity is actually at 20. And for present value, it's always the beginning of the annuity. In this case, it's time 0. So PV is at time 0, AV is at time 20. That is why I need to accumulate for 20 years, not 19. Okay, that's good for this part. In the next video, we're going to study 3.7. That's continuously varying payment streams. That's more complicated.